Well, thank you, Roland. I'm turning around looking for that person you're talking about. I don't really. uh, Thanks for painting me in such a nice, flattering light. Uh, Colin, Sarah, everybody, Will, thank you so much for everything you've done to help host me here. I'm just going to start. Before I say anything, I want to acknowledge, because I forget to do this sometimes, and I can't do it, the generous donors that we have at the Smithsonian Tropical Research Institute for our research. Roland and his family, the Hoax, have been very generous in helping support the core of Agua Salud and particularly the smart reforestation research. Stanley Mota, Frank Levinson, and his family. We've received lots of funding from National Science Foundation, the Heising-Simons Foundation, lots of different groups, and we're very grateful for them. I also want to point out, which probably would be obvious to you, is that we couldn't do it. It takes a village. Couldn't do it without a lot of teamwork. There's a whole host of incredible technicians, Panamanian technicians, botanists, and hydrologists that work on our projects, as well as we're basically had an army of students. And I believe we've even had a tough students. So if you are interested, interns and PhD students, postdoctoral fellows, visiting scientists that get all the work together. Roland mentioned the Agua Salud project, and that's kind of the umbrella within which we do this smart reforestation research. In Agua Salud, we study the ecosystem services provided by tropical forests in a seasonal climate, how they change with land use and climate change. And we try to go beyond the relatively simple, but by no means trivial effort of measuring ecosystem services to understand how the ecosystem functions so the team can build the next generation of models. And of course, one of the big services, or one of the big things we all hear about in terms of climate change, is carbon sequestration, the global climate carbon cycle. If you read any of the Intergovernmental Panel on Climate Change reports, you might believe, like I do, that we're in a climate crisis with climate change. And tropical forests are a vast reservoir of carbon. So obviously, when you cut a tropical forest, it releases carbon dioxide through burning or through decomposition. And the cutting of the tropical forest has increased phenomenally the amount of CO2 in the atmosphere. That doesn't let us off the hook with transportation. All of us in the United States and all the emissions that we do are pretty high too. So the first thing, how do you measure carbon in the forest? Well, I mean, we quantify it, and we do this with destructive sampling by the best way of harvesting trees, weighing them fresh, drying them, developing allometric equations and how to measure it. And so scientists have become pretty good at measuring carbon. And punchline to this of how much carbon is in the forest, we have about 440 metric tons of carbon dioxide equivalents in a mature forest in central Panama. If you're just getting into the research and thinking about carbon, you might want to realize that, understand that the scientists, we often talk about carbon, C. Policymakers talk about carbon dioxide equivalents, CO2 equivalents. So if you're paying attention to reading what you're reading and things, you have to understand if somebody's talking about carbon in the forest or carbon dioxide equivalents. So if you read our papers about the mature tropical forests in Panama, you'll see that I'm talking about 120 tons of carbon, 440 tons of carbon dioxide equivalent. So we live and work in rural Panama. Well, I live in the city, but we work in rural Panama. And our team, we're interested in, there's lots of people who are studying carbon dynamics, the stocks and the fluxes of how carbon moves through an ecosystem, mature forest. And we're out really kind of in the messy, it's not messy unless you get mud on your boots, but the rural landscape. It's kind of where the action is. It's where the rubber hits the road. It's where people live. And so, and this is where, when people are talking about forest restoration to help mitigate carbon, because trees grow, and as they grow, they take CO2 out of the atmosphere. This is where it's going to happen, where people actually live. And so we've measured, as Roland pointed out, we have lots of studies. So we've measured the carbon in the soil. We've measured the carbon in trees. We've measured the carbon. We've actually excavated trees to figure out how much carbon is in the roots. We've got the coarse woody debris, lots of different pools of carbon, but we're interested in how it's distributed across the landscape. And this would be a cattle pasture, a wooded cattle pasture, or in a secondary forest, or in some other land use. So we claim to have the largest study of tropical forest restoration. The key there is of its kind. We're not diminishing the kinds of studies that everybody else does, but a big portion of what we do is that we look at the intersection of hydrology, forest interaction on water cycle, and carbon and forest dynamics. So in our study site here, this is, and you can't see it very well, but there's Sober Indian National Park follows this red line, these red lines here. This is a mature forest area. We're in, Panama City, if you don't know, is on the Pacific Ocean. I didn't actually know the first time we went there, but it was a conference. I knew that before I moved there. And we're up in this area, and we're in the Panama Canal watershed. And that gives us an excuse really to study hydrology in ways that other people can't. The Panama Canal works on fresh water. And so we want to understand the interaction of the forest dynamics and carbon. But here you have all these lines. These are all plots, forest plots that we've set in across our landscape, which we've put in the land that we control. So around these red areas, and this is land that donors have purchased, so for our use to do this research. We at the Smithsonian Tropical Research Institute, that, as Roland pointed out, we've been there 100 years, actually. The Smithsonian has been there for 100 years. And one of the features of research in Panama is long-term research. So not just a 1 or 2 year study. And so as scientists, we're pretty darn happy, right, Colin? If you get an NSF grant for 2 years, you're high-fiving people, and that's really great. But you can do a 2 year study, but you might miss the most important thing that happens in the life cycle of a forest. So this project was set up to be a 40+ year project. After that, even before that, it's going to be somebody else's problem, or better yet, playground, if I will. So we have these plots. Well, you see here, 0 to 8 years, 9 to 16, 17 to 14. So this is a chronosequence. So it's a time for space substitution. So if we want to understand secondary forests, you could put a plot in, you could measure all the trees, and you could go back there every year for 100 years, and you know a lot about secondary forest regeneration. But we don't have that kind of time, although people do it. What we do is we put in plots in different ages of forest. So you might have a 2-year-old forest, a 5, a 9, a 12, an 18, 36, whatever, and you make the big assumption that what is the 2 will become the 4, will become there's a linear kind of a change in the dynamics. And we know that not to be true. There's lots of reasons it wouldn't be, because of, the idiosyncratic prior land use of one particular plot. Maybe there were cows on it, maybe somebody dumped chemicals on it, maybe it's in some other kind of way. But we have a high replication of any age class. And here we've just grouped them. These are not all, they're all within these kind of classes. And this is just to show you that we have quite a broad spread of plots across our landscape. So we want to be able to say what's going across the landscape. If we put all the plots in one area, it would be what we call pseudo-replication. You know a heck of a lot about one tiny area, and you couldn't extrapolate it to anywhere else. These white squares here, these are part of our native species plantations. And I will also, here's our teak plantation. I'll say something about that a little bit later. So in our plots, we have 54 sites. We have an upside and a downslope plot. This actually does not even include these black liana removal plots. We have been privileged to be able to get the resources to measure these trees most years. And so young forests are really dynamic. There's a lot of action, a lot of winners and losers competing for light and soil and nutrients, and a lot of mortality, a lot of recruitment. And so you really kind of need to measure them every year. And we've measured 130,000 individual trees over 10 years. We're further beyond 10 years now. We have about 1.2 million individual measurements. And this is why I gave the shout out to those incredible technicians and students and everybody, the army that goes out and measures these. We have 600 species of trees and lianas in this forest, in these plots. And I can identify about 2 of them. It's incredible botanists that are there that really can nail them. And so we've also, and this is what's important for us, is we've, over this time series, we've caught the flood of record, which I'll talk about a little later. After one of the wettest years on record, we had this massive rainstorm, and we've caught the biggest drought of the century. And so those are the perturbations, the things that are going to really knock up the forest, and it's going to drive some of the community dynamics and ecosystem dynamics. So a 2-year study, we could have done a study of secondary forest regeneration, and we think we know something about it. But if you miss the most important event, which for us, the droughts come in El Nino years. So we're kind of bracing for what's going to happen this year. Maybe it will, we will have this will be the second worst drought on record. It looks like it's shaping up like that. So on this graph, so, you know, what are we doing in terms of measuring our carbon, just for the carbon dynamics plot? This is a graph. We've published a paper with basically this data in it. Here on this axis, you have AGB. This is above ground biomass. So we measure the biomass, and about half of the biomass, the dry biomass in a tree is carbon. So we know how to make that calculation. That's simple enough. And then you have stand age in years. So if you would have seen from those other, that previous graphic, that most of our plots are in these really young forests. And that's because that's where they're so dynamic. That's kind of where the action is. And here on this graph, you can see, so you got gray points. Okay, that's good. And you got these lines. And these gray points is how much biomass was in 2008. And the lines are the remeasurement every year since then. So here you have it looks like there's a tree fall gap or something happened and carbon dropped and it went up. So you have these, you know, any given plot can be doing something very different. If you only have a handful of plots, you might have one here and somewhere here, and you might have a growth curve that would look very different than this. So that's that high replication gives us great confidence. In fact, we've done some modeling, extended this out, even out to Barrow Colorado Island, which is where one of Smithsonian's gems for tropical research, where there's mature forest, and this graphic actually nails spot on the carbon or biomass that we'd have in a 300 to 500 year old forest. So we're looking at secondary forest, and if you actually don't know what secondary forest is, or many of you probably realize that most of New England's forests are secondary forests, right? You know, with agricultural, when it moved west in 1900, a lot of forests kind of regrew, but there was quite a bit of agriculture. That's why you see stone walls all through the forest, right? Because they were all fields back in the day. So there hasn't been as much study of these naturally regenerating secondary forests, and like I said, we're doing quite a bit on. And we know that our secondary forest captures over the first 30 years. So instead of having that growth curve, if we just drive a straight line, it captures 6.9 metric tons of CO2 equivalents per year in above ground tree biomass. We've also calculated and published on what we call ecosystem carbon, because we have excavated roots. We have measured the soil compartment. Actually, most carbon in a forest is in the soil in a tropical forest, but it's in low concentrations and most of it's not mobile. We have measured coarse woody debris. We have measured lianas, so we know what we have. And we do that, we have 60% more carbon in those other compartments. So if you have 100 tons, you know, per hectare in above ground biomass, you really have 160 tons of carbon in that forest. So we have had a lot of collaborators. So these graphs, they may or may not look impressive. They're impressive to me. There's a lot of really important data that goes into this. So this is the carbon comparison we're going to talk about in the canal region of, this is where the Panama Canal goes through here, from Panama City through to Colon. In this region, which is about 25% of central Panama. So we're able to start, you know, our Agua Salud plots where we've measured carbon. They helped anchor an algorithm that a colleague, Greg Asner, who used to be at Stanford, the Carnegie Airborne Observatory, now Arizona State, developed a new algorithm for measuring carbon with LIDAR. So LIDAR, you fly an airplane, you measure it with a laser, and that algorithm is now used all over the world. Greg and his team then flew Panama and came up with the first ever map of a country of all the carbon in the vegetation. So we have a really good estimate of how much carbon was in that vegetation. Another colleague, a woman named Kendra Walker, she did painstakingly detailed work to use Landsat imagery to look at land cover maps of the whole country of Panama from 1990 to 2020 every single year. And what's different from her work in the Global Forest Watch, which is a global coverage of land use change and deforestation, is that she actually has an error around her estimate. So you can have some confidence of what you kind of know. So from that basis, we were able to then, with other colleagues from the Harvard Forest, Jonathan Thompson and his group, run a spatially explicit model of, and you know, do a recent trends deforestation. So from 2015 to 2020, we knew what the correlates were of, you know, closest to river, more deforestation, or urban areas, or what it would be. and we spatially drove that deforestation. And then we used that previous graph to grow the forest because we knew the carbon baseline over time. And so from 2020 to 2030, you can see that we actually will lose about 37,000 hectares. Well, we hate to lose any forest, but with the recent trends, not so bad. But we'll gain 27,750,000 tons of CO2 equivalents. And so just for you, I looked up, maybe anybody know how much the city of Boston emits per year? I looked it up. Well, I could only find 2020. It's 6.2 million metric tons. So this is the equivalent about 3.5 times of what the city of Boston's emissions are. So this just shows, most of this forest was really young, and so it's just growing like crazy on infertile soils and sequestering a lot of carbon. But then we also did a scenario, we call it our accelerated development, or here it just says prior 2000. 2000, of course, is the new millennium, but it's also when the Panama Canal was turned back to the people of Panama from the US government, and deforestation stopped coincidentally, or because of that, was reduced by over 80%, the rate of deforestation. And so we flipped back to that and we drove that forward. And you can see that we'll lose over 175,000 hectares of forest through 2030 if we go back to previous rates of deforestation. And we'll lose, 10.5 million tons of CO2 equivalents. So there's, you can gain 27 or lose 10. And that's really the window that brackets what policymakers, the decisions they make, and local, decision maker stakeholders, their daily decisions, what they would do. And this is not, this is entirely possible. There's talk of new paved roads through here. There's a big mine, which is why Panama is actually shut down right now because of protests, clearing massive areas of beautiful forest. Oh, whoops. Am I going forward? Yeah, so here we fast forward to 2050, and you can see that, we'll have almost 52 million tons of carbon. That's almost 9 years of emissions to the city of Boston again. But the other side of it, if it goes forward, the green is forest, the white is not forest. And so the difference is 125 million metric tons, depending on which way the decisions go. Fortunately, we're going in this direction right now. And the governor of Panama actually, I'll say claims, I can't back it up, that they're actually carbon negative, that they're actually, in the country of Panama, sequestering more carbon than they're emitting. That emit, but they don't admit that it doesn't include airplanes, and it doesn't include all those ships that go through the canal, which to go through the canal, you get a Panama flag. It becomes a Panamanian flag vessel, right? So anyway, but they're doing better than most, right? This is a teak plantation. And so we started smart reforestation is rolling, our tagline, he's got it, plant the right trees in the right place at the right time for the right reason. This was not planted in the right place at the right time. We kind of knew this. Our teak plantation, we weren't trying to learn about the silvicultural or the biological characteristics of teak. People have known about that for 100 years. What we wanted to understand is its relation to hydrology. This is not growing particularly well. So in comes with smart reforestation. So with a colleague who's my PhD advisor, Mark Ashton at the Yale Forest School, started studying the silvics, the basic ecological characteristics of a lot of native tree species. There's basically 4 species or genera that are planted throughout the tropics. You have acacias, you have pines, you have eucalyptus and teak. And there's some others, but 75% of what's planted in Panama is teak. The reason people don't plant native species, one of the main reasons, they just don't understand how to germinate the seeds, how fast the seedlings grow, where they grow, all that kind of stuff. So we've been working on that for 20 years, and we know quite a bit by now. That's kind of scary, 20 years. Where will you be in 20 years? Well, it might be in Panama. On this graphic here with smart reforestation, a thematic kind of, conceptual idea. We have biomass here, but it could be, reforesting for whatever ecosystem service you're interested in, increasing biodiversity, or maybe it's for, hydrology or some of the reasons. But we're really focused on infertile soils. And the reason for that is, we have over 8 billion people on the planet today, and several billion live in the tropics, and a lot of people depend on their land to cultivate their crops to live on. And so we reason that all the fertile soils will go for agriculture or some other high value product. And so all of these discussion of reforesting the tropics to try to help mitigate climate change and take CO2 out of the atmosphere, it's all going to happen on infertile soils. And it's not trivial to plant trees on those. So almost any tree will grow well on a fertile site. There are a few actually won't, but the idea here is if you have a tree that grows well there but not infertile, depending on the site, you might get more biomass over time. So infertile, intermediate fertility, fertile. And so we're focused really on this infertile side. And so what we want to do is through our different mixtures and monocultures, different kinds of treatments, see if we can push whatever this service would be here on the left up to kind of what we get in an intermediate fertility soil if you're getting, need higher biomass or towards a fertile area. So that's kind of what we're trying to do in part with smart reforestation. But we reforest for a whole host of social objectives. Some people want fruit trees, some people want water retention, some people want just want forest for biodiversity, and we try to look at mixtures and different treatments for different reasons. This is the Aguas Lima native species in 2008 plantation, and you can see that if you look really closely here, you see lots of little dots, and those are all seedlings. That year we planted. I used the royal we. I planted only a couple of 140,000 trees. This is our secondary forest catchment. There's a couple plots in here. So, and we have weirs down here, little dams where we're measuring stream flow over time here. And here you have a Terminalia amazonia. This tree grows incredibly well on really low phosphorus soils. So there's kind of the conventional wisdom is that, temperate forests are limited by nitrogen and not enough nitrogen to keep driving the dynamics, and tropical soils are limited by phosphorus. Now we have colleagues that have turned that on its ear, but Terminalia amazonia or amarillo grows really well on low phosphorus soils, which is one of the major constituents of life and soils. And this is a 10-year-old Terminalia amazonia. Terminalia amazonia in 30 years will gain 220, a monoculture of it will gain 220 metric tons per hectare of CO2 equivalent. So 30 years, half of what a mature forest has if you plant for that. So if you just want to plant for carbon and you're feeling lucky, you might plant a monoculture of Terminalia amazonia. But if some sort of an insect attack comes through or some sort, you might really regret that. But it is a pretty fabulous tree in terms of its carbon sequestration. It grows straight, so it's a good timber tree for multiple use, not super high value, and so it's a nice one to think about. Here, Victorino Montenegro, he's one of our colleagues who works with us, Carlos Diaz. They're planting a Dalbergia retusa, and I'm sure that Roland's heard me talk about cocobolo. Cocobolo is a really valuable craft wood, and the press reports say it can be worth up to $10,000 a cubic meter. I've seen kind of bill of ladings where it was bought and sold for $3,000 a cubic meter. Your mahoganies are about $500 a cubic meter in the best of cases. So this is way over what other woods are sold for. It's used for specialty woods, for guitars, for carving, for lots of things like that. When grown in the right place, I mean, this is a 20-year-old Dalbergia retusa. It's not one of ours. Ours are better. No, ours aren't 20 years yet. But it's really high wood density. It sequesters a lot of carbon, but it doesn't grow as big as a Terminalia amazonia. But depending on what you're interested in, if you think big is better, well, you might be interested in Terminalia. But if you care about value, we did a little estimate about this stand, which is not multiple hectares, but it's worth several $100,000 per hectare at $3,000 a cubic meter. So it's massively valuable compared to the Terminalia. Okay, back to our teak plantation. Well, we did plant it to try to understand the hydrology part of it, but we also decided we kind of learned enough, and so we discussed with some people who were helping to finance our project the idea of converting it. We wanted to undertake a new experiment to see if we could return an underperforming teak plantation to productivity, so biological productivity, growth, and as we often measure in biomass, and profitability, because the original purpose is really planting a plantation like this is to drive economic value for the landowner. And so we set up an experiment where these 6 species that have different values. This one here is one that produces little fruits, and people make a sweet drink out of it in Panama. So we just trying to see, we do what we call enrichment planting. We planted these trees into the teak plantation, and kind of relying on the teak to be what we call nurse trees. So for the cocobolo, we want to see if we can get it to grow nice and straight like the one I showed you, which often doesn't. And then, you know, we have these plots around, and we also added a fertilization treatment just with local fertilizer you can buy off the shelf. The reason for that is because, you know, this was an applied experiment, and, you know, people wouldn't have access to any kind of special nutrient mix that we might want to come up with. And so here you can see this is actually me holding a Dipteryx panamenensis or oleiferae. And this tree is 5 or 6 years old, and this is next to a 14-year-old teak tree. So the Dipteryx is already pushing up through the canopy. It's already as big as the teak in most places. It just happens to be 8 years younger. So it's growing. It definitely is suited for the site. And so, you know, probably what would happen over time is that the teak that are here will just be kind of cut in I want to say relejo, in a thinning. They'll be thinned out, and they wouldn't, you know, in this instance, they wouldn't really be commercially valuable. But these other trees would be over time. And Catherine Sinecor, who's a postdoctoral fellow who works with me, we have a paper that's just going to come out in Nature Communications doing an economic analysis of various restoration treatments on infertile soils with subsidies and carbon payments. So hard to see this. Well, let's focus in a little bit here. We decided to take that enrichment planting on the road, and that was in our teak plantation, and we planted in rows here. We cut, this was a pasture that was left to regrow, a neighbor in Agua Salud, and we're actually paying him $130 per hectare just to let his forest regrow. And then we're planting in these high-value timber species into this area, and we're going to manage them. We're managing them the first several years. The Panama Canal Authority is financing the actual planting and management of that. So they're a huge partner in all of this. I should have mentioned that. And so this is just new. And I mean, it's about 2 years old. We're out there remeasuring. And, you know, part of it is to the carbon payments. The $130 per hectare comes from the Panama Canal Authority. They're paying people $130 per hectare to protect mature forest. And so they're doing it more for water reasons. We're doing it for the carbon. It comes out to, with our forest growth model, about $18 a metric ton of CO2 equivalent. So is the forest a sponge? Well, a lot of the bingos, the big NGOs, conservation NGOs around the world, have been selling the forest as a sponge for decades. You know, the tropical forest absorbs water in the wet season, releases it in the dry season. You have higher stream flow in the dry season than you do in the wet season. As I learned when I started working at the Smithsonian, tropical hydrologists were not at all in agreement. There were big arguments in the literature. I mean, you know, you can imagine an argument in the literature. Well, he is unfortunately wrong, or this article, you know, Hall et al. Made a mistake. No, anyway, it's not that's a raging argument, right? So we had 3 hydrologists start out on this project together because they're really interested in understanding if the forest really is a sponge or not. And this image drives it home. This is Lake Bayanu, but actually, if you were in the Panama Canal watershed, Gatun Lake looks like this. At some point, they're artificial lakes that were created by flooding forest, and all of these trees really should be underwater. But because of the drought and the dry season, they're kind of perking up. And so, you know, access to abundant, clean, fresh water is really one of the biggest development challenges of this century. And so, in a lot of rural areas, you know, access to dry season water is really what can drive survivorship for your livelihoods. So we're very interested in this, and lots of cities all over the tropics depend on fresh water from the mountains, and, you know, how the land manages above them is pretty important. So is the forest a sponge? Well, here's a graph to help answer that. This is from 2013, and sorry, it's in Spanish, but this is, you know, your season, estación seca, dry season. So enero hasta mayo, so from January through May, which is our dry season. Escorrentía, this is stream flow. in cubic meters per hectare. And the bosque is a forest, and the potrero, that's a pasture. And you can see that there's the line above, the top line is the bosque, is the forest, and the red line here is the pasture. And the area in between here, the difference, that's the sponge effect. So we do have a sponge effect. This is from 2013. It was published in a paper. We published again in 2019 with some colleagues on economic analysis in the Proceedings of the National Academy of Sciences. We consistently find a sponge effect, and it's about 15% increased dry season flow. But remember, trees use water. They use more water for evapotranspiration than grass do. So you have to, it's about regulating stream flow and, you know, on both sides. But if you plant up, as some people have suggested, the whole Panama Canal watershed, you'll actually have less water going into the canal. And right now, because they're increasing lake capacity, the excess water wouldn't just run off. They can actually put it in these lakes. So it's you have to think about both sides. But too much water can also be a problem. And so we've probably, if you read the papers, and I don't chastise you if you don't read them anymore, because it's a lot of depressing news out there. But there's been lots of big floods around the world. Lots of big problems by too much rain. We're getting tropical rain in Seattle and California, these big raindrops that come down, and you know, New York City just had a big flood, right? And that was because they didn't have enough capacity to evacuate the amount of water they were getting in the time period they were getting it in. So in 2010, at the end of what was one of the wettest years on record, we got the flood of record. It's believed to be about a 500-year storm in the Panama Canal watershed. We got 300 millimeters overnight and 500 millimeters during the week. Lakes were already full. In the Panama Canal watershed, there's a lake called Alajuela Lake, which they store all the water for the dry season. The dam on that lake is Madden Dam, and it was already at the specifications it was built to withstand. And so the Panama Canal Authority had to actually close the canal for shipping. They opened up all the locks and all the spillways to try to evacuate as much water as safely and as efficiently as possible to try to save the canal. So imagine if that dam would have burst, then not only the water, I mean, all the water in the lake would have flooded downstream into the canal, and probably would have destroyed the canal. So what we have done, we actually have the same soils and geology as the Upper Chagres National Park, which is a forested park above Alajuela Lake. And so we did a thought experiment. Let's deforest, let's apply the excess water we had in a pasture, which we did have excess water, to that 100,000 hectare national park. And if we did that, we estimate that you would have 100,000 additional cubic meters of water that would have hit that dam right when it was ready to burst. And when I say this, I always say, even if you don't know what a cubic meter is, 100 million of anything is a lot, right? But a cubic meter weighs a metric ton, right? So imagine 100 metric tons of water at force hitting that dam right when it was about to burst. So we believe that Chagres National Park saved the Panama Canal, actually. And so that is an incredible ecosystem service of mitigating the worst of flooding. Forests are not going to eliminate flooding. And at the end of the day, the worst effects of flooding is depending on your slope angle and your intensity of your rainfall, but they can help mitigate that. And so people say, oh, it's a one-off, a 500-year storm, right? Well, guess what? In 2012, we got the next biggest storm, and there was loss of life in the Panama Canal watershed with roads washed out. And then in 2016, we just missed getting our first ever hurricane in Panama. And that's because we didn't get the hurricane force winds, but we got the rainfall. It was another superstorm. So 3 biggest storms of basically the century came within 6 years of each other. So that's where, climate scientists are, one of the predictions of climate change is more frequent severe weather events, be it drought or floods. And we certainly seem to be experiencing that. So in terms of forest restoration, well, here's another thematic kind of conceptual model. This would be just the dry season, dry season stream flow. How can we recover it? So I've convinced you, I hope, that a forest has more water in the dry season in the stream than a pasture does. So that's just the dry season. This is the total dry season stream flow. And what we're trying to do is to see if, whoops, there we go. If there's ways that we can reforest to try to, restore that sponge, if you will. that dry season. And so here we've just, yes, okay, I put secondary forest succession down here and some sort of reforestation. Hopefully it's intelligent, maybe it'll not be. But what we know is that when you plant trees, initially the forest, it actually might have well, we've seen this in lots of places, you might have less stream flow for a number of years because those trees are using a lot of water. So the trick here is to see, when you cross this line of what you had in pasture, so you see a decrease and then the increase. And my colleague, Bob Stollard, has 10 years worth of stream flow that I really hope we're going to publish soon because we have these different land uses and you can actually see some signals. So what happens here, this is Helmut Elzenbier and his team from Potsdam University led this research looking at infiltrability here, KS. This is a kind of a measure of the ability of water to infiltrate into the soil, because that's the first step. If it's going to store it, there's a reservoir, and for the dry season, it first has to infiltrate. And a cattle pasture is really compact, and so it doesn't. It mostly runs off downhill. So we've measured every year in a pasture here to a forest through 2016, and these are not very deep here. The measurements where these cores were pulled, and you can see that in 2008, okay, not much change. But then you see over time in our secondary forest that infiltrability, in fact, does change quite a bit in both the real close to surface layer and the slightly below that. And we don't exactly know why it's overperforming forests here. Pretty interesting, but it could be because there's lots of roots right near the forest soil, right near the top of the soil, and that it's enhancing groundwater infiltration. But the really cool thing for us about these graphs, and I drive this point home, is that you can imagine if you're approaching a politician or a policymaker and say, you really should do this because in 100 years, we're going to see this really important change. Like, who is going to do that? Especially in today's climate, right? And not because of climate change, because, well, there is climate change and heating up in the capital, I guess. But if you can do something in somebody's administration, if you can show a difference in 4 years or 5 years, like we can here, you have a lot more traction in convincing them to actually invest if it's for reforestation, for restoration, for groundwater infiltration. Our native species plantation, well, we have the same pattern. The blank areas here is we just didn't have money to measure everywhere every year, so we kind of switched off in the year. So we see this, we've kind of learned the teak plantation actually has the same. So whatever method of planting trees, everywhere we've planted them, we see this pretty rapid recovery of infiltrability. It isn't observed everywhere in the world, but it is observed on our clay soils. So we're pretty keen on this. Andrew Birch, who does PhD at University of Colorado with Holly Barnard and Bob Stollard, has followed track stream flows using chemical tracers to try to understand the reconstitution of the sponge and linkage stream flow. And he's found after 8 years in our secondary forest, we have a sponge up to 30 centimeters. There's already the same flow paths, the same plumbing, if you will, has been recreated. So we think that's pretty cool. Let's go to the videotape. So the key with the growing human population, there's less, well, there's not less space in the world, but there's less space per person, right? So you have to be much more efficient in your land use planning and your use of the soils of the area. So we have lots of pastures. We've done lots of research there. Lots of work in naturally regenerating secondary forests, which I don't have. It's fun to think about corridors because here you have a living fence, right? And a living fence can be a biological corridor for certain kinds of animals. So if you want to have connectivity, and a colleague of mine took and sent me a video, we have a sloth in Agua Salud crossing the road, and sloths are not meant to be on land, right? So it's kind of going like this and like this, get across. But it went across to our living fence, and then it used the fence to go off to the forest. So that was pretty cool. Okay, so we've taken Agua Salud on the road, if you will, our smart reforestation, and this is thanks to some support from the Mark and Rachel Rohr Foundation. And we're working in an indigenous area, the Nobe Bugle Comarca. Comarca is an indigenous semi-autonomous area in Panama. In order to work there, we spent a year during COVID of doing our free prior informed consent. to get permission to work with people and to understand. We did 14 trips out there, brought people to see us. This is at one of the meetings, and this is here because this is the Comarca All-Star team, actually, in my view. Francisco Herrera is a Panamanian social scientist who's been working up there for over 40 years. And if it was not for Francisco, we would never have had the entry into the Comarca. At the same time, when we got permission to work there, the Peace Corps and the Japanese cooperation, international cooperation, got turned down from these people because they have been misled and mistreated, if you will, by lots of different groups. And so they don't want to just let anybody work there. So thanks for Francisco. And really his a good friend is Camilo Ortega. And Camilo, so the Comarca, the indigenous area, it was indigenous kind of territory beforehand, and it was created as a Comarca, and he's really the father of the Comarca. And so we have the president of the Traditional Congress. So we're working with the traditional leadership there to do our forest restoration, and it's an experiment. So we planted out over a 450 square kilometer area. We planted out different plots and species mixtures where we're testing species, but we're also testing carbon payments. And so Mark Rohr has given us upfront, because I told him I would not do this unless he would give me carbon payments for 20 years. Because if you're out there raising money for something, everybody wants to have, to do the first few years, the first sexy thing, but nobody's going to come in and pay a year 5 to 20 of somebody else's project. So Mark has generously given us the first 20 years of carbon payments, $130 per hectare per year, to continue this project. And we're doing the research, to understand the dynamics and working with these local people. So as I said, we went to them, and we also brought them to Agua Salud to see kind of the big experiment, to understand what we're doing. And this, like I said, it was during COVID, and we're talking about secondary forest dynamics here with a group of visitors from the Comarca. It's a beautiful area. It's not an easy area to reforest. I mean, it's kind of a large area in arrested succession. It can all support forest. It's all in the Holdridge life zones of forest, and you find lots of pine stands throughout the whole area that were planted 40 years ago, really tall, forests. But for a variety of reasons, there's not a lot of forest. It's absolutely, if there was no light in here, believe me, these photos are gorgeous. And it's a lot of fun to do that. And I found out I'm not nearly as good a shape as I would like to be, because hucking up these mountains in 100% humidity, well, anyway, I've shown that I'm not as young as I used to be. So it's a really beautiful area. So this is a project where we planted over a year ago the first set of 50 hectares, 50 more hectares this year. And we're just waiting for the rains to settle so we can move around here a little bit more easily logistically to measure those plots. So that's what I have for you. I went longer than I thought. Thank you very much for your attention, and I'd be happy to take any questions.
Thank you so much, Jeff. That was fascinating. And I will open it up to questions. If you want to raise your hand, I'll bring the mic to you.
Thank you for the very interesting talk. My question was around the communities who've been living there for generations. So in your research, are there ways you incorporate their knowledge and their generational wealth of knowledge with respect to afforestation? And I'm sure there are a lot of practices around how they approach forests. So is there a way that interacts with science and your research?
So yes, in the project we started 20 years ago, there was a postdoctoral fellow who's doing social science research and trying to understand how people use forest, how they value trees and all that. A few publications came off that, some really interesting work. One is that in Panama, people are willing to make long-term decisions even with just squatter rights. They don't have clear land tenure. Lots of countries, governance is such that people will not do that, but they will there. Here in the Comarca, we have new partners from Oregon State University, Reem Hajar, who's on faculty there, who works on community forestry around the world, a postdoctoral fellow, Hasmin Gonzalez is coming. So they're going to be doing studies socioeconomic baselines, which include environment, how people use the forest and value it, and also a big one on governance, because the governance of that comarca is challenging, in part because the local leaders, the traditional leaders, refuse to let the national government in and international corporations do copper mining and all these things they want to do. They tried to bribe them. They tried to give them cars and houses and everything else. So, and they refused. And I've been to the same people who were offered these bribes. I've been to their incredibly modest houses, right? So you have leaders all over the world who are willing to accept all kinds of money, but these guys, weren't. And so as a consequence, the Panamanian government under President Martinelli years ago did what what the government of China did to Tibet and the Dalai Lama. They kind of pushed out the traditional leadership and put in their own comarcal leadership. So the Dalai Lama is kind of it. And so I may not know exactly what I'm saying, but anyway, so there's this kind of government installed leadership. The comarcal leadership took it all the way to the National Supreme Court. They actually won the case, and the government's still working with them. Different other leadership. So we need to understand social science, these great plans of planting trees and doing all this work. If you don't, you have to work with people. You have to do it one landowner or one, person at a time. And that is one of the things. It's traditional knowledge is important, but it's one of the things that's missing from a lot of these discussions of let's restore, let's plant the whole, forest around the world. There's a lot more needs to be done than that. Yeah, thanks.
Hi. So something that I've been looking into relates to post-industrial contaminated areas called brownfields. And I'm wondering if, especially since you're looking into infertility and creating more fertility in these spaces, if smart reforestation and some of these concepts could also be applied to contaminated areas, such as contaminants might be lead, arsenic, oil, etc. If this kind of method could also be a solution.
Yeah, I mean, basically, it's an umbrella of research, and the research and those kind of things, definitely has to happen. And so there's a Peruvian postdoctoral fellow who worked with me, Francisco Roman. He's now down, in Puerto Maldonado in Peru, and the mining, the gold mining there is they just use vacuum cleaners. They dig up the streams and they use lead to extract the gold, and it's just the whole area is awfully contaminated. And he's doing research on trying to restore or reforest those mining sites. And so you're finding species that will have the tolerance for the lead and all the other chemicals, and just will grow. And then so yeah, and there's another initiative to do some of this kind of work in Indonesia that we're talking about getting involved in. Yeah.
I have a quick question. So I've been reading a lot about these flying rivers they've talked about in the Amazon. So the trees releasing a lot of atmospheric water that then comes down in place. And so, I was just reminded in droughts, sometimes I would imagine that they're really worried about actual having enough water in the canal. So to what extent is the hydrology that's created in the air that allows for more rainfall being factored into your models, if that's clear?
So, for sure. I mean, Doug Shields is doing a lot of work on the atmospheric rivers in the Amazon and other places, and about how these really large atmospheric circulations that bring it's a conveyor belt, water. Our rainfall is really driven. The Panama is a small peninsula. There's orographic uplifting, so when the warm air rises, it kind of rains, and we don't really have that phenomena where we are. But it's interesting that a lot of people still don't believe it's a thing, right? But there's really good data to show that these atmospheric rivers kind of exist. So the evapotranspiration from our trees is really not going to be dropped anywhere close to where we are. Probably where with 80 kilometers wide isthmus, it's not.
Gotcha.
I could be wrong. I'm just dismissing it, just like some of the other, but.
Well, I guess there was a publication a few years back where they were saying that deforestation in the Atlantic lowlands of Costa Rica might be affecting the amount of rainfall that's hitting the mountain range down the middle of Costa Rica. And I was trying to understand sort of the scale of what effect deforestation has, and so to the sort of atmospheric water. So even if it's not going to fall right there, what is the impact of the forest cover writ large on rain in the Panama area is sort of my question, I think.
Yeah, I mean, so I don't know. But we have this, so my gut feeling is that we have this incredibly moisture-laden air that comes from the Pacific or from the Atlantic that blows in, and the amount of ET, my guess is not as significant, but I could be wrong, and we're not studying it. I do worry when some people talk about reforesting the whole Panama Canal watershed, though, what that will be. I don't think it's certainly not going to fall in the watershed, and we'll have less water there. So, but if some bright, young, tough student or faculty wants to come down, and good, let's do it.
Well, we have another question here.
Jeff, that was great. I'm wondering, with use of native tree species, are there many leguminous nitrogen-fixing trees that would raise their fertility faster?
We're using a lot of N-fixers. I mean, so we have a whole program that I didn't talk about with Sarah Batterman from the Carey Institute. Sarah's PhD research was showing the importance of nitrogen fixers done in Agua Salud. She had a Nature paper on this in terms of the supply of nitrogen from just a small group of trees. About 3% of the trees supplies enough nitrogen to account for the missing nitrogen to allow for those trees to grow so fast. So we do, and we have a whole experiment where we're looking at nitrogen versus phosphorus limitation, adding nutrients, and hopefully the first papers, well, there's the first paper, there's one in review in Nature Ecology and Evolution, another one's going to Nature very soon for review, hopefully. So we look at that. We've also in our plantation looked at N-fixers and look at nutrient acquisition. So looked at both trees that excrete phosphatase, which is an enzyme that will help acquire phosphorus, and looking at the nitrogen fixers. And not all N-fixers fix at the same rate. And so, there's not one model organism. Delbergia retusa, this cocobola, actually fixes nitrogen like nobody's business. So we're pretty keen on that. What still remains to be seen is the N-fixers. Are they contributing it directly to the ecosystem through leaf fall? Or are they pulling it back in through, retranslocation, using it kind of for their own growth initially? But they can certainly help increase the biomass. There's a paper that we have with Lars Heidienst, Levi Varon, and Nature Communications using Earth system modeling or force dynamics with N-fixers or without it, and what the consequences would be for biomass production. But there's just no way we're going to fertilize the world's forests. We have to find ways of using, incorporating native species and mixtures to try to enhance growth. Yeah.
Okay.
Just to wrap up, really cool research. Do you guys host undergraduate or graduate students through the RU program or any other program to go there to do some research in the summer?
So we at STRI get approximately 1,400 visitors a year. We're scientific staff of about 30. There's, the incredible publications that we have per year is driven by visitors. And so we have, many hundreds of interns that come. We don't have an RU program per se right now, but we have our own internship program that twice a year people can apply to do internships at STRI. We have a short-term fellowship program where people can do their own research program and work with us. We have a PhD, a postdoctoral fellow program. So we have lots of money that people can apply for to come and join us to do research. Yeah.
Well, I hope one of you might apply for one of those positions, and we'll come back and report on your experiences. Thank you, Jeff, for a fascinating talk. I'm feeling much smarter. Thank you. And if you have any questions, I'm sure he'd be happy to just answer them if you have any burning questions you want to ask in private. Thank you.